Steady heat conduction. This chapter discusses heat conduction under steady state conditions, where temperature does not change with time. The main focus is how heat flows through walls, cylinders, and multi-layer systems in one-dimensional and multi-dimensional forms. The concept of thermal resistance is used as the main analysis tool. This approach simplifies the calculation of heat transfer rates in real systems. The discussion links conduction physics with electrical circuit analogy.
Lesson plan: Heat transfer. This lecture structure places steady heat conduction as a continuation of basic concepts and the heat conduction equation. This topic serves as a bridge towards convection, radiation, and heat exchangers. Each chapter is connected through energy balance and heat transfer mechanisms. Understanding this sequence is important to ensure consistent thermal system analysis. This topic forms a foundation for more complex thermal system studies.
Learning outcome. The learning outcomes emphasize the ability to build thermal resistance networks for practical conduction problems. Students are expected to analyze multi-layer walls, cylinders, and spheres under steady conditions. The concept of thermal contact resistance is introduced for real interfaces. The role of insulation and cases where insulation may increase heat transfer are also discussed. In addition, fin analysis and shape factors become important engineering applications. Heat transfer through a wall. Heat transfer through this wall is assumed to be one-dimensional because the temperature changes only in one direction. The temperature profile decreases gradually from the hot side to the cold side. This condition indicates a steady-state system. The wall boundaries are kept at constant temperatures, so the heat flux remains uniform. This model becomes the basis for most flat wall conduction analyses.
Steady heat conduction in a wall. Under steady conditions, the temperature profile inside the wall is linear with respect to position. This indicates that the temperature gradient is constant throughout the wall thickness. Because the gradient is constant, the heat transfer rate is also constant. The temperatures at both surfaces are fixed, so there is no energy accumulation inside the wall. This model simplifies the relation between thermal conductivity and heat transfer rate.
Thermal electrical analogy. Heat flow can be analogized to electric current that flows due to a potential difference. In thermal systems, temperature difference plays the role of voltage difference. Thermal resistance acts like an electrical resistor that opposes the flow. The relation Q equals T1 minus T2 divided by R is similar to I equals V1 minus V2 divided by R. This analogy is very useful for building complex thermal resistance networks. Convection resistance at surface. At the wall surface, heat is transferred to the fluid by convection. This process can also be modeled as a thermal resistance. The magnitude of this resistance depends on the heat transfer coefficient, surface area, and fluid conditions. By including convection resistance, the heat flow path from solid to fluid can be analyzed systematically. This approach unifies conduction and convection in one thermal network.
The answer is B, the temperature difference, surface area, and heat transfer coefficient. Explanation of incorrect answers. A. Incorrect. The thickness of the solid material affects conduction, not convection. C. Incorrect. Fluid density affects buoyancy, but does not directly control convection resistance. D. Incorrect. Thermal conductivity affects conduction, not the resistance in convection heat transfer.
Convection and radiation resistances. On a real surface, heat is usually lost by convection and radiation simultaneously. These two mechanisms work in parallel, and each has its own resistance. The total heat transfer rate is the sum of the convection and radiation contributions. The parallel resistance approach simplifies the analysis of these two interacting mechanisms. This model is especially important for high-temperature surfaces. Thermal resistance network. This system shows a combination of convection resistances on both sides and conduction resistance inside the wall. All these resistances are arranged in series, so the heat transfer rate is the same through each element. Temperature drops occur step by step across each resistance. The heat transfer rate can be calculated using Q equals T infinity 1 minus T infinity 2 divided by R conv 1 plus R wall plus R conv 2. This network is conceptually identical to a series electrical resistor circuit. Thermal resistance network. This system emphasizes that heat transfer through a wall involves conduction inside the material and convection on both surfaces. All these mechanisms can be represented as a series resistance network. Each resistance causes a temperature drop proportional to its value. This concept simplifies visualization of the heat flow path in real systems. The electrical analogy helps explain how total resistance controls the heat transfer rate. Mathematical identity. This mathematical identity explains that if several ratios have the same value, the ratio of the sum of numerators to the sum of denominators remains the same. This principle is used to simplify the analysis of temperature drop distribution in resistance networks. With this approach, contributions of each resistance can be combined mathematically. The numerical example shows that proportionality is preserved. This concept is important for distributing temperature drops in multi-layer systems. Thermal resistance and temperature drop. The temperature drop across each layer is directly proportional to its thermal resistance. This means layers with higher resistance experience larger temperature drops. Under steady conditions, the heat transfer rate through all layers is the same. The total temperature drop is distributed among the resistances according to their proportions. This principle is the basis for determining interface temperatures in multi-layer systems. The temperature drop across a layer is directly proportional to its thermal resistance. Two-layer thermal resistance. A two-layer wall system consists of two conduction resistances and two convection resistances at the surfaces. All these resistances are arranged in series along a single heat flow path. Each conduction resistance depends on thickness, thermal conductivity, and cross-sectional area. The total resistance is the sum of all individual resistances. This model represents many practical multi-layer wall applications in engineering. Two-layer wall with temperature points. The temperature at each interface can be calculated using the heat transfer rate and the relevant resistances. For T1, the relation Q equals T infinity 1 minus T1 divided by R convect 1, 1 is used. For T2, the relation Q equals T infinity 1 minus T2 divided by R convect 1, 1 plus R wall, 1 is applied. For T3, the relation Q equals T3 minus T infinity 2 divided by R convect 1, 1 is used. This approach shows how internal temperatures can be determined systematically. Temperature evaluation in two-layer wall. Surface and interface temperatures are determined based on the distribution of thermal resistances along the heat path. Each temperature point reflects the accumulated temperature drop from the hot side. Since the heat transfer rate is constant, each temperature drop is determined only by its resistance. This resistance network provides a very clear picture of temperature distribution. This approach is very practical for multi-layer wall design analysis. The interface temperature T2 is determined by considering the combined resistances of convection and the first wall. Thermal contact, ideal versus actual. In ideal thermal contact, there is no temperature drop at the interface, so T1 equals T2.
In real conditions, surface imperfections always introduce contact resistance. This causes a temperature jump at the interface. The heat flow paths also become non-uniform due to microscopic gaps. This phenomenon is important in mechanical joints and assembled components. Thermal contact and heat flow. Perfect contact produces a smooth temperature distribution without any discontinuity. In contrast, imperfect contact creates a sharp temperature drop at the interface. This contact resistance originates from surface roughness and limited real contact area. As a result, the overall heat transfer rate becomes smaller than in the ideal case. This effect must be considered in precision thermal system design. Thermal contact resistance setup. This apparatus is designed to measure thermal contact resistance between two solid specimens. The system consists of heaters, thermocouples, and heat flux meters to monitor heat flow. A mechanical load is applied to ensure realistic contact at the interface. Cold fluid is circulated at the base to maintain controlled temperature boundary conditions. With this setup, the effect of contact pressure on resistance can be analyzed quantitatively.
Thermal contact conductance is strongly influenced by the type of fluid at the interface. Fluids such as glycerin show much higher conductance compared to air. Besides fluid type, surface roughness and contact pressure also play important roles. The better the medium fills microscopic gaps, the smaller the contact resistance becomes. These data show the importance of selecting interface media in thermal design. The answer is answer C. High conductance fluids, like glycerin, improve heat transfer. Explanation of incorrect answers. A. Incorrect. Air, being a low conductance fluid, does not enhance heat transfer effectively compared to high conductance fluids like glycerin. B. Incorrect. Surface roughness and interface pressure significantly impact heat conductance and cannot be ignored. D. Incorrect. The type of fluid and its conductance is a critical factor, while the thickness of the plate impacts conduction within the plate, not the fluid interface.
Effect of coatings on conductance. Metallic coatings, such as nickel or aluminum alloys, can significantly increase thermal contact conductance. Increasing contact pressure always enhances conductance for both coated and uncoated surfaces. The type of coating affects performance, with tin or nickel alloys showing better results. This shows that surface engineering is very important in thermal management. Mechanical joint design must take this aspect into account.
Thermal resistance in parallel layers. In this configuration, heat flows through several paths simultaneously. The amount of heat flow in each path is determined by its resistance value. Layers with smaller resistance carry a larger portion of the heat. The total heat transfer rate is the sum of all parallel paths. This model is often used for walls with different materials arranged side by side. Series parallel thermal network. This system combines parallel and series resistances in one network. Part of the heat splits into parallel paths, then recombines and passes through series resistances. Each element still follows the basic thermal resistance laws. The total resistance is calculated by mathematically combining series and parallel rules. This configuration is very common in real insulation systems. Thermal contact conductance data table. This table shows variations of contact conductance for different metal pairs and surface conditions. Materials such as copper exhibit very high conductance, especially under certain surface conditions. Surface roughness and pressure strongly influence the obtained values. The difference between identical and dissimilar metal pairs is also clearly visible. These data are important as references for thermal joint design. Thermal contact conductance. Copper shows the best conductance performance compared to other materials. Smoother surfaces generally provide higher conductance. Under vacuum conditions, conductance drops drastically because heat transfer paths are reduced. For dissimilar metals, the aluminum-copper combination gives the best results. Contact pressure remains a key factor in all cases. Aluminum-copper combinations demonstrate the highest conductance in dissimilar metal pairs. Heat loss in a pipe. Heat transfer in a pipe occurs radially from the inner surface or wall to the surroundings. Because of the cylindrical geometry, the problem can be simplified to one-dimensional in the radial direction. Heat loss is mainly determined by convection at the outer surface. This situation is commonly found in steam pipes or hot fluid pipes. This model becomes the basis for pipe insulation analysis. Heat transfer in cylindrical shell. Heat transfer in a cylindrical shell occurs radially from the inner side to the outer side due to temperature differences. The thermal resistance is determined by the shell geometry, material conductivity, and wall thickness. Under steady conditions, the heat transfer rate is constant across the entire section. The temperature profile is no longer linear with radius, but logarithmic. This model is very important for pipe and tube analysis. Thermal resistance in cylindrical shell. This system combines inner convection resistance, cylindrical conduction resistance, and outer convection resistance. All these resistances are arranged in series, so the heat transfer rate is the same. Heat flows from the hot fluid through the cylindrical wall and is released to the cold fluid. Each part contributes a certain temperature drop. The total resistance determines the overall heat loss. Heat transfer in composite cylinder. A composite cylinder consists of several material layers arranged concentrically. Heat must pass through each layer sequentially, so the resistances are in series. Each layer has different thermal conductivity and thickness. The contribution of each layer strongly affects the total system resistance. This model is commonly used for multi-layer pipes and insulation systems. The answer is answer B, the thermal conductivity and thickness of each layer in the system. Explanation of incorrect answers. A. Incorrect. Color and texture do not directly affect heat transfer. Thermal properties like conductivity and thickness are key. C. Incorrect. Convection plays a role at the inner and outer surfaces and cannot be ignored in a multi-layer system. D. Incorrect. Uniformity of heat distribution is a result, not a cause, and is influenced by the layer's thermal properties and resistances. Steady heat conduction in layers. In one-dimensional steady conduction, the heat transfer rate through all layers is the same. Each layer experiences a temperature drop proportional to its thermal resistance. The total temperature drop is the sum of the drops across each layer. Therefore, adding a new layer always increases the total resistance. This principle is very important in thermal insulation system design. Insulated cylindrical pipe. This system consists of a pipe covered with insulation to reduce heat loss. Its thermal resistance network includes conduction through the insulation and convection at the outer surface. Adding insulation increases conduction resistance but also increases the outer surface area. The heat loss rate is determined by the combination of these two effects. This analysis is important in industrial pipe design. Critical radius of insulation. Adding insulation to a pipe does not always immediately reduce heat loss. Up to a certain radius, heat loss may actually increase because the convective surface area increases faster. This radius is called the critical radius of insulation. Beyond the critical radius, adding insulation will reduce the heat transfer rate. The critical radius value depends on insulation conductivity and the convection coefficient. Cooling function of Stegosaurus fins. The fins of Stegosaurus are hypothesized to function as a means to dissipate body heat to the environment. The large surface area increases heat transfer by convection and radiation. This structure allows more effective body temperature regulation. This concept shows that fin principles also apply in nature. This biological analogy helps in understanding fins in thermal engineering. Heat transfer in radiators. Radiators use thin fins to increase the heat transfer surface area. With a larger area, heat can be transferred more effectively from the coolant to the air. Interaction with airflow significantly enhances convection. This design allows high cooling performance within limited space. This principle is widely used in vehicles and engine cooling systems. Thin plate fins maximize surface area, increasing heat transfer from coolant to air. Innovative fin designs. Innovative fin designs aim to maximize surface area while optimizing airflow. Different shapes can increase cooling effectiveness without significantly increasing volume. Compact structures allow application in limited spaces, such as electronics and machinery. Each design is tailored to specific application needs. This approach shows the importance of geometric engineering in heat transfer. Heat transfer in finite element. Heat flows by conduction along the fin and is dissipated to the surroundings by convection. The analysis is performed using a small differential element as a control volume. Fin geometry, such as cross-sectional area and perimeter, strongly influences the heat transfer rate. An energy balance on the small element is used to derive the fin differential equation. This approach forms the basis of all fin analyses. Boundary conditions for fins. The temperature at the fin base is usually specified and kept constant. The fin tip condition can be adiabatic, at a specified temperature, or subject to convection. In the assumption of an infinitely long fin, the tip temperature is considered equal to the surrounding fluid temperature. The choice of boundary condition strongly affects the temperature profile solution. Therefore, the model must match the real physical condition. Temperature profile of circular fin. The temperature profile in a fin decreases exponentially from the base toward the tip. This decrease reflects the balance between conduction inside the fin and convection to the surroundings. With a uniform cross-section, the analysis becomes simpler, and the solution takes an exponential form. The base temperature serves as the main boundary condition of the system. This profile shows that most heat is dissipated near the base. Steady heat transfer in fin. Under steady conditions, the heat conducted into the fin base must equal the heat dissipated from the fin surface. There is no energy accumulation inside the fin. Heat loss occurs continuously along the surface by convection. This ensures that the heat flow rate inside the fin decreases along its length. This energy balance principle forms the basis for fin performance evaluation. The answer is answer B. Heat conducted into the fin base equals the heat dissipated through its surface. Explanation of incorrect answers. A. Incorrect. In steady-state conditions, there is no heat accumulation. Heat flow is constant throughout the fin. C. Incorrect. Fins enhance heat transfer, allowing heat loss to the surroundings, not preventing it. D. Incorrect. Surface heat loss depends on surrounding conditions, such as the convection coefficient and ambient temperature. Corrected fin length. Since the fin tip also loses heat by convection, the effective fin length needs to be corrected. This approach replaces the real fin with an insulated tip fin having an equivalent length. In this way, the calculation becomes simpler without significant loss of accuracy. This method makes it easier to compare fins with different boundary conditions.
The corrected length concept is very practical in design.
Effect of fins on heat transfer. Adding fins significantly increases the heat transfer surface area. With a larger area, heat can be dissipated more effectively by convection. This improves thermal performance without increasing the operating temperature. Fins become an efficient solution to enhance cooling in limited spaces. This principle is widely used in many cooling systems. Temperature distribution in fins. In the ideal case, the fin temperature is assumed uniform, but this is not realistic. In real conditions, the temperature decreases from the base to the tip due to heat loss along the fin. This decrease makes the region near the tip less effective in dissipating heat. Therefore, fin efficiency is always less than 1. This temperature distribution is important for understanding fin limitations. This section serves as a transition toward the discussion of fin efficiency and different fin profiles. The next focus is how geometric shapes affect heat transfer performance. Comparisons among profiles will show the trade-off between material usage and thermal performance. The efficiency concept will be used as a quantitative measure. This transition links basic analysis with practical design.
Efficiency and profiles of fins. Fin efficiency is strongly influenced by geometry, thickness, length, and material conductivity. Rectangular fins are easy to manufacture and suitable for many general applications. Triangular and parabolic fins offer material savings while maintaining good thermal performance. Circular fins are widely used on pipes and cylindrical components. For complex geometries, Bessel functions are used in efficiency calculations.
Bessel functions are used in fin efficiency calculations for complex geometries under steady-state conditions.
Efficiency of straight fins. This graph compares the cooling efficiency of 3 fin shapes: rectangular, triangular, and parabolic. The vertical axis shows efficiency, and the horizontal axis represents a combined factor of shape, size, and material properties. As this factor increases, efficiency drops for all 3 types. The blue parabolic fin is the most efficient because its curved design uses less material where heat transfer is lowest, while the green triangular fin is in the middle, and the orange rectangular fin is the least efficient. In engineering, while the parabolic shape saves the most weight and material, it is harder to manufacture, so designers must weigh thermal performance against production costs.
Fin efficiency comparisons. Efficiency comparisons show that triangular fins are generally more efficient than rectangular fins for the same amount of material. Parabolic fins provide performance between the two. As fin length increases, efficiency tends to decrease because the tip region becomes less effective. Profile selection is a trade-off between thermal performance and material usage. This analysis helps determine the most optimal shape for a given application. This section marks the transition to a specific discussion on annular fins and their applications. The focus will be on the effect of radius ratio and thickness on efficiency. Circular geometry requires a slightly different analytical approach. The previously discussed concepts still serve as the foundation. This transition links general theory with cylindrical geometry cases. Annular fin efficiency insights. Annular fin efficiency decreases as the outer to inner radius ratio increases. Constant thickness produces predictable efficiency patterns. Materials with high thermal conductivity always provide better performance. Fins with radius ratios close to 1 show higher efficiency. Annular fin design must balance surface area expansion and heat dissipation effectiveness. Fin effectiveness highlights. Fin effectiveness measures how much the heat transfer increases compared to a surface without a fin. This value is strongly influenced by material conductivity and geometric shape. A good fin should have an effectiveness much greater than 1. If effectiveness is low, adding a fin becomes uneconomical. This concept helps evaluate whether using fins is worthwhile.
The answer is B. Thermal conductivity and geometry of the fin play a significant role in its effectiveness. Explanation of incorrect answers. A. Incorrect. Material properties, such as thermal conductivity, are critical for efficient heat transfer in fins. C. Incorrect. While convection is important, fin geometry and material properties are equally significant in enhancing heat transfer. D. Incorrect. Fins increase surface area, which enhances, not decreases, heat dissipation.
Surface area. Highlights. The base area without fins is determined by the geometric dimensions of the main surface. When fins are added, some area remains uncovered and is called the unfin area. The total surface area increases drastically due to the contribution of fin surfaces. This increase in area is the main source of enhanced heat transfer. Therefore, surface area calculations must be done carefully. Temperature impact on heat transfer. Near the fin base, the temperature difference with the fluid is still large, so the heat transfer rate is high. Toward the tip, the fin temperature approaches the fluid temperature, so the heat transfer contribution decreases. The middle region provides a moderate contribution. This shows that not all parts of the fin work equally effectively. This phenomenon explains why fin efficiency is always limited. Heat transfer variation. Shorter fins can only transfer a limited amount of heat because their surface area is small. When the fin length is increased, the heat transfer rate increases, but not linearly. For very long fins, the increase in heat transfer becomes very small. Beyond a certain point, adding more length provides almost no additional benefit. This phenomenon shows that there is a practical limit to fin length. Beyond a certain length, additional length minimally impacts the heat transfer rate. Heat sink comparison. Different heat sinks have different thermal resistance values. A lower resistance value indicates better heat dissipation capability. A larger surface area generally improves cooling performance. Installation orientation, such as vertical or horizontal, also affects convective performance. Therefore, heat sink selection must consider geometry and installation conditions. Conduction shape factors. Shape factors are used to simplify two-dimensional and three-dimensional conduction analysis. Their values depend on geometry and the position of heat sources, such as buried or parallel cylinders. Spacing, size, and orientation strongly influence the shape factor value. With shape factors, heat transfer rates can be calculated without solving complicated differential equations. This approach is very useful for complex geometries. Extended conduction shapes. For cylindrical and spherical layers, the shape factor changes according to dimensions and material interfaces. Corner and wall junction cases can be simplified using special factors. For buried disks and spheres, depth and insulation conditions strongly influence the conduction path. This approach allows quick estimation of heat transfer rates for many real configurations. This extends the application of the shape factor method in engineering. The answer is B, depth and insulation, which influence the conduction path. Explanation of incorrect answers. A, incorrect. Shape factors are relevant for cylindrical and spherical layers, but do not specifically address buried disks and spheres. C, incorrect. Corners and edges apply to adjoining walls, but are not directly related to buried geometries. D, incorrect. Material color does not impact heat conduction. Thermal properties like resistance and depth are key factors.
References. This chapter refers to the main textbook by Eunice A. Chengel and Afshin J. Gajar as the source of figures and concepts. This reference is an international standard in the field of heat transfer. All models and approaches used follow the established formulations in that literature. Using this source ensures consistency with global engineering practice. This chapter concludes the discussion of steady heat conduction in a comprehensive manner.